Hello, everybody. I will try. I forgot my pointer, but anyway, if anybody has it, I would appreciate. But let me ask you, most of you are grad students? Okay. Anybody had any course in nuclear physics, reactor physics, or anything like that? A few people. Okay. Excluding professors. Okay. So basically, I will try to cover. There is a lot of material that I would like to tell you, but if you have any questions and something is unclear, just stop me. These are my colleagues that also contributed partially by giving me some of the slides. So I will try to cover a little bit about Department of Nuclear Engineering because we are the only one in California, so at least you should know a little bit about us. Then I will go over current energy situation in the US as well as in the world. Try to convince you why do we need nuclear energy. Look into what happened in 2005 with the new energy policy in the US. Hopefully the next administration will not turn everything upside down, which happened a few times in the past. So it's why we need to have a long-term energy policy in this country. I will talk about what happened after that, which I called Renaissance in Nuclear Energy in this country. GNEP, or Global Nuclear Energy Partnership, and what is going on in the rest of the world. And a little bit of summary what I consider when I say sustainable nuclear energy for sustainable society. You can hear all the time sustainable society, but very little about sustainable nuclear energy. This is just about the department. We are celebrating 50th anniversary this year, and we have one of our faculty here, Professor Olander, is just sitting on the back, and he is also celebrating 50th anniversary of his service to UC Berkeley. So these are different chairs of the department. I just took over in 2005. As you can see, two famous people from Lawrence Livermore and Lawrence Berkeley National Laboratories actually suggested in '59 that with two national laboratories, nuclear laboratories nearby, UC Berkeley needs to have nuclear engineering department. We did have trigger reactor in our basement, so most of you probably didn't know that. We are in Echeverry Hall. Our underground laboratory is below Soda Hall, so they built Soda Hall on top of it. It is true, and we lost our parking place. So we did have trigger reactor until late 1980s. It was the commissioned. City of Berkeley was not happy with that at all, and we had demonstration at that time. I was told I came later. We still do have that containment structure that you can see here. You can visit us and see it. But we use it now for the largest rotating target neutron source, which is the deuterium-tritium accelerator to produce 14 MeV neutrons. Pretty strong, 2 times 10 to the 11 neutrons per second per milliamp of neutrons. We do have all kind of other laboratories in Echeverry Hall. These are our faculty. I will not go over. They cover large areas that I listed on the second slide. So we are a small department, but we do cover all these different areas, and you are welcome, to come. We have Monday colloquia, and those are pretty interesting as well. So going from fusion and fission energy to fuel cycles, radioactive waste, materials, risk safety, nuclear thermohydraulics, bionuclear engineering as well, and medical application of radiation. These are some of the issues that are of great importance for this country, such as use of nuclear energy not only for production of electricity, but also for hydrogen production that I will talk a little bit about. We are very much involved in homeland security, in terms of radiation detection and measurements. Both of these fields were neglected for the last 30 years. So now, when we need it, suddenly we are invited by both Department of Energy, Department of Homeland Security to produce results in no time. It is not possible, so, but we got large grants, and I will talk about it. This is biomedical use of radiation, and our department is involved in both medical diagnostics and radiation therapy. And here you see all kinds of industrial uses of radiation. I will just mention a few of the recent research project that our department got funded. The first two that you see are from Department of Homeland Security, DNDO, total of about almost 10 million for next 4 to 5 years. So we are really looking for both grad students and postdocs to work on these type of projects. Okay, now I'm switching into sustainable society. From my point of view, we cannot have sustainable society without sustainable energy, and from my point of view, sustainable energy cannot avoid having nuclear energy and something that I call sustainable nuclear energy that can produce cheap, abundant, secure type of energy, both for us and for the rest of the world. And you can read the definition of sustainable society that I found in our competition in MIT's book on sustainable energy, choosing among options. So we do need energy. So let's just see what is prediction by Department of Energy in this country. So by 2020, we might need 44% more electricity just for US. What is our current situation? 50%, to be exact, 52% of electricity is supplied by coal, which is the dirtiest technology so far. 20% by nuclear energy, and one nuclear power plant that you see is the Diablo Canyon nuclear power plant in California, run by PG&E. 7% is hydro, and only 2% are renewables, less than 2%. So if we look what's going on with global climate change, you could see model and observation that do not match in the first diagram if you only include climate changes due to natural causes. However, if you also include natural causes plus human-generated greenhouse gases, then they do match. And if we go to this diagram, when we have concentration of greenhouse gases such as carbon dioxide, methane, and nitro oxides, we see exponential increase starting just about 1750, when we have the beginning of the Industrial Revolution. So it could be connected with human influence. This is another interesting slide which gives information about the life cycle analysis of greenhouse gas emissions, from including construction as well as everything. So these are grams of carbon dioxide equivalent per kilowatt hour, and you have coal, gas, hydro, and everything else, including nuclear. So you see which types of energy sources produce majority of greenhouse gases. Hydro, you might ask how hydro produces methane and whatnot. Well, for hydro, you need to flood large areas with biomass that will start decaying and then emitting all kind of methane and so on. So this is the current picture in the US that I already mentioned. If we include sources of electricity that are emission-free, so we have different pictures. 72% almost is nuclear. Then we have hydro, geothermal, and very little wind and solar. So those that are advocating replacing everything by renewables must think about what we could do, because the only baseload electricity production sources are nuclear and coal. So if we can replace those two with renewables, I will be very happy, but it is not possible. So this is the picture in California. This is actually, if you look into your PG&E bill every month, they include flyers in which they explain this structure. So you will see so-called eligible renewables that include biomass, geothermal, small hydro, solar, and wind. And then the rest is, as you can see, PG&E reduced coal, increased natural gas, and nuclear is a large percentage of PG&E's mix of electricity. This is the picture of where 103 nuclear power plants in the US are located. You can immediately see Midwest and East, very little on the West Coast, very little in California. And when we are talking about California, California is the only state that has ban on the construction of new nuclear power plants. And it is in the law, and a sentence, I think, is something like no new nuclear power plants could be built in California before permanent solution for radioactive waste is found. Having in mind that Yucca Mountain is still not constructed, and I will talk about it, we still have that ban. I was in Sacramento just 10 days ago, last Monday, a week from last Monday, testifying in favor of nuclear energy. One of California Assemblyman Chuck DeWar is trying to push bills to remove that ban. This is the second year he's trying that. Last year, Per Peterson went there. This year, I went there. Who is the chair of the Committee on Natural Resources, Lonnie Hancock, former mayor of Berkeley. Her husband, Tom Bates, is now mayor of Berkeley, so they just changed their roles. So she went to Sacramento, and he came to Berkeley. So as long as they're there, nothing will change. So I don't want to say anything else. But this is the mix for the rest of the world. So you can see that in most of the countries, we have 20 to 30% of electricity production. In France, is up to 80%. However, Australia, you could see Australia, 92% is coal. And Australia is very rich in terms of uranium. 40% of world reserve of uranium are in Australia, but they're just building their first research reactor, Opal reactor, so we will see how it will go. So this is the picture of the rest of the world. So you see North America, you see Europe, and Japan and Korea mostly. So these are developed countries. So developed countries do rely on nuclear energy, while developing countries now, like China, India, are going in that direction. So again, in China, we have that 99% almost electricity is produced by coal. So it's very polluted, and it is also a huge question mark for the Olympic Games. And I was in Beijing about 10 years ago, and it was very, very polluted. So we will see what will happen. This is comparison what went on over the last 20 to 30 years in the rest of the world. So yellow is the rest of the world continued to build. In the US, we had two peaks in mid-1980s and 1970s and 1980s. So this is the dates when nuclear power plants started operating. After that, very little. So we haven't constructed a new one for about close to 30 years. This is the world view. So currently, there are 435 nuclear power plants in the world. It's about 16% of world electricity production. 28 are under construction, and 222 are planned. Mostly, as you can see on the right, in Asia. There is one in Europe, in Finland, now under construction. France will continue to construct. A little bit in South America and the rest of Europe. So this is the numbers and total percentage of generation. So in the US, 20%, France 78%, Japan 25%, South Korea 40%. So you see what is the percentage in different countries. In terms of price, it's hard to see, but blue is oil and gas, so they're kind of peaking. This is not including last 2 years. And you see nuclear is red and coal is yellow. So in terms of production price, in about 1999, 2000, nuclear production cost of electricity, nuclear went down below the production cost of coal. So right now it's about 1.6 cents per kilowatt hour. So it's pretty cheap. And then when we are talking about renewables, I'm definitely for solar and wind. But if we want to include the real cost of power sources affected by capacity factor, meaning what is the percentage that they are actually producing electricity during the day. So you see that coal and nuclear are 80, 90 and over, gas 30%, hydro, fuel cells, wind and solar thermal or photovoltaic is about 25 to 30%. So it's still pretty low, and if we calculate this capacity factor and turn into a number of dollars per kilowatt electric produced, including that, then the price goes really up if your capacity factor goes down. So I invited Patrick Moore about a year ago to come to our department and give a talk. I don't know if anybody came. It was December, I think, or 6th. As you know, he was a Greenpeace founder. He split with the Greenpeace movement about probably 15 to 20 years ago. And he showed, during his talk, he showed Radical himself from the 60s and 70s, long hair and whatnot, and saving everything. And then he mentioned that when he realized that they were always against something and they were not for something. And when he realized if they would continue adding what they're against and what is the cause of that, he said the only solution that is really the good one is to get rid of human race. Then all evils will be solved. And then he split, and now he has his movement. But he basically testified in April 2005 before the House Government Reform Energy and Resources Subcommittee, saying that nuclear energy is the only non-greenhouse gas emitting source that can effectively replace fossil fuels and satisfy global demands. And then at the UN Climate Change Conference the same year in Montreal, he said that energy decision must be based on science, on facts, and so on, not on politics and emotions. So he was calling his former colleagues and friends just to rely on science and facts, which is probably impossible. Again, what is the difference for different sources of energy? This is a busy slide, but I will just point out a few things. So this is nuclear fission. So we have uranium-235, for example. We have neutron coming, adding a little bit of energy to destabilize the nucleus. So nucleus splits, and each nucleus splitting will release 200 mega electron volts of energy in terms of kinetic energy of fission products. So if we are talking about fission fuel energy density, it is 8.2 times 10 to the 13 joules per kilogram. So what would be fuel consumption by 1,000 megawatt electric nuclear power plant? 3.2 kilograms per day. This tells you something when we are talking about waste as well, how much waste we will be producing. And all the waste that has been produced by 103 nuclear power plants in this country, if we were to move everything to Yucca Mountain will be filled. It is about 70,000 metric tons of waste. But it is pretty small because of high density of the fuel as well. So 3.2 kilograms per day. And these are different products, radioactive waste and whatnot that we deal with. In terms of energy from fossil fuels, energy density is 2.9 times 10 to the 7 joule per kilograms. So 10 to the 13, 10 to the 7, we have 6 orders of magnitude difference. And it immediately tells you what is the difference in coal that you need to have per day for the same 1,000 megawatt electric plant. And then here you have nitro oxide, sulfur dioxide, ash, carbon dioxide that will be also produced. And people do not know ash is pretty radioactive because of natural constituents of coal as well. Fusion. Again, this is still in the future, but we get another order of magnitude 10 to the 14 joules per kilogram, and we have 0.6 kilograms per day consumption of the same size of power plant. So again, comparison. This is the Nuclear Energy Association. You have a different type of fuel on the left. You have how much of coal, natural gas, and whatnot you need in order to replace 1 kilogram of uranium fuel. And you can compare immediately. So you will need 4,000 wind turbines to replace 1 kilogram of uranium. And you need about 70 square kilometers of solar panels to produce the same energy. So this is kind of the difference in energy density. So this is one fuel element that you have, and you have the train of coal. So with all of that, and with all kinds of issues in importing gas and oil and instability in the world, and the need to have energy independence and energy security in this country, in 2005, Congress, after 5 years of infighting, finally came up and kind of proposed and accepted a new energy bill. And these are some of the issues that contributed to that particular decision-making process. So let's see what is in it. So this is Energy Policy Act of 2005. There are several different issues, investing in infrastructure, ensuring reliability of transmission, delivering diversity of fuels. And then in terms of nuclear energy, this policy act was to jumpstart both new plant construction that was neglected for the last 30 years and research and development in nuclear energy and nuclear technology. So we are very much behind the rest of the world, and even if we were to start constructing right now, we have all the permission and let's do it, we don't know how, because we lost the ability to basically construct nuclear power plants in this country. So we need to get a reactor vessel from Japan. Japan is now the only country that could do that. Okay, so there is a long line, waiting list of different countries trying to do that. In addition, we had 2 vendors, Westinghouse and General Electric. They haven't constructed in 30 years anything in this country. They were going around the world and doing that. Now Westinghouse has been sold to Toshiba, nuclear part, and General Electric and Hitachi are working in collaboration. So in any case, Japanese companies will be building new nuclear power plants in this country. So in terms of jumpstart of new nuclear power plant construction, this Energy Policy Act gave a lot of incentives to nuclear industry, because nuclear industry got burned in the 70s and 80s, and they're very reluctant to go back unless government gives them loan guarantees, risk assurance, production tax credit. So they got all of this from the federal government, and it's why they started doing something about it. And in terms of research and development, this is work on the next generation of nuclear power plants, and I will talk about it. Nuclear hydrogen production is a very important part, because heat is byproduct in electricity production in nuclear power plants, so we could use that heat for thermochemical production of hydrogen. Then Advanced Fuel Cycle Initiative is back. Basically, if we could close the fuel cycle by introducing recycling and reprocessing, that this country did not do since Carter times. President Carter basically said no reprocessing, no recycling. We will not do that. We will have once-through fuel policy, meaning you have fresh fuel, you take it out and you store it somewhere. Other countries, including France, Japan, China, Russia, Great Britain, they do reprocessing and partially recycling, but we didn't do it. So that has been changed. Also, nuclear engineering programs, because the field was neglected, new people were not coming into the field. So now we have a huge problem. Everybody is trying to hire nuclear engineers, but there are not very many of them. A lot of them retired in the previous years. Now both Westinghouse and General Electric are hiring new people. Westinghouse hired 900 engineers, not only nuclear, but including nuclear last year. And I got a list from them that in the next 5 years, they will need 500 engineers per year. Nuclear Regulatory Commission, because of all the license, applications for license that are coming through, they're hiring 300 engineers at this moment, including national laboratories and whatnot. Also, medical isotope production, we have a lot of problems in domestic production of nuclear, medical radioisotopes, because this country shut down almost all research reactors over the last 30 years. During the dry period of, let's say, Clinton administration, about 50% of nuclear engineering departments were shut down because there was no support for them. Research reactors were shut down, no support from Department of Energy, and suddenly, when we need all it back, we cannot produce enough nuclear engineers in these times. So this is, I will not go over all these different details, but just to point out that in March of last year, Nuclear Regulatory Commission approved its first ever early site permit for excellent Clinton nuclear power plant site in Illinois, and only a few weeks later, also they approved this early site permit for Entergy's Grand Gulf nuclear power plant site in Mississippi. So what is good in this case is that many of licensed nuclear sites have space for more nuclear power plants, meaning the license was for more than one, maybe two, maybe 4, 5 nuclear reactors. However, because of the problems in the 70s and 80s, they were not constructed, but they still have license. So they don't need to go through painful process from 30 years ago to fight with local groups of citizens, concerned citizens that were suing everybody. So since Energy Policy Act of 2005, nuclear industry suddenly woke and they realized that there is a potential of huge profit for them. So they started all kind of different consortia. There are probably 10 by now of different consortia. And they, starting in October of 2006, they started announcing that they will submit applications for license of so-called combined construction and operating license. At that time, there were 19. By now, there are 36. And I will show some of the sites. There are mostly 3 designs that I will show. One is new design by Westinghouse, which is 1,000 megawatt electric AP 1000. It has design license. It got it about a year ago. Not a single one was built in this country, but having in mind that Westinghouse nuclear part was bought by Toshiba, and Toshiba bid in China and won, so they won, and they might build 4 of these, first in China and then maybe in the US. GE has this ESBWR, which is 1,500 megawatt electric. And we have French company, Areva, which is very active, and they want to build European-type EPR reactor. These first two, and I will show in a minute, are so-called passive safety generation 3+ reactors. EPR is still active safety generation 3 reactor. And also Texas, company from Texas, NRG, wants to build advanced BWR reactors that were already constructed in Japan. So probably that might be the first one to be constructed. And my estimate is, if everything goes as predicted, because NRC is required to process a license within 3 years from the moment license is submitted. So maybe we will have some new reactors operating by 2014. So these are some of the sites, the current ones. And you can see AP1000, 12 of those, EPR5, ESBWR6, and some of the generation 3 reactors are also being planned. So mostly east and southeast part of the country, not much on our side. So this is a small cartoon that I usually show to my students. So this is the operation of boiling water reactor. Unfortunately, what we do, we are using nuclear energy to boil water. Efficiency is about 30% for these type of reactors. This is pressurized water reactor, pretty similar, although we do not allow water to boil, so it is pressurized water. So we have the separate loop with steam generator and then turbine and generator, and everything else is the same. So this is to show to you what are the differences in different type of reactors. On far left, you have generation 2. So these are mostly PWRs and BWRs reactors that were built in this country. Then you have generation 3 with active safety. So you have all kind of active safety mechanisms. So this is French, which is being built in Finland at this moment. And advanced BWR reactor, several of those were built in Japan, Taiwan, and around the world. And these are generation 3+ passive safety type of reactors. You see how small they are? Much smaller because they're using either natural circulation or different type of passive safety mechanisms. So you don't need to have huge active safety, as you can see in EPR reactor. So they're pretty small. Passive safety means that you are using the physics, more or less, to shut down reactor if any of the factors, temperature or power, increasing beyond what you predict. These are plans for new construction. So France is continuing. They want to build the next generation, which is so-called generation 4, by year 2020. Russia is planning to have 30 to 40 new reactors by 2030. China also at least 30 by 2020. India as well, and other countries. There is discussion in Europe as well. This is a new program which was announced about a year ago, Global Nuclear Energy Partnership, which basically tries to reduce spent fuel. We don't call it waste because it has still a lot of fuel in it, uranium and plutonium, that could be taken and burned back in, and produce electricity. So we want to recycle nuclear fuel. We want to improve impact on the environment, reduce dependence on foreign fuel and whatnot. So this is what I already mentioned for GNEP. But what is important in GNEP is basically advanced nuclear fuel cycle. So we want to close it so that very little actually goes underground. We want to reprocess spent fuel, take out whatever is still useful and put it back and burn in different type of reactors, such as burning plutonium and all kind of minor actinides, use nuclear power to produce electricity and hydrogen, and come up with new designs for the next generation. So if we don't do anything, Our current plants will slowly shut down starting 2010 because their licenses will expire. If we have full relicensing, then they might continue for another 30 or so years. If we start building generation 3 reactors, this is the picture, and then with generation 4, and then using hydrogen for transportation, so this is additional power that we could add. So GNEP, or Global Nuclear Energy Partnership, includes the rest of the world as well. So the idea is that we have nations that do have nuclear technology, and then we have other nations that do need cheap electricity, but we don't want them to have nuclear technology. So these are kind of user nations, and these are fuel supply nations. So the idea is to have small type of simple type of reactors for those countries. So countries that do have nuclear technology will provide fuel and reactors, take back spent fuel, and then do recycling and reprocessing, and include something called advanced burner reactors to burn all those long-lived radioactive nuclides that should not go underground. So this is what that generation 4 nuclear reactor should do in terms of economics, proliferation resistance, sustainability, and safety and reliability. And this is what the new fuel cycle is supposed to do. So we are trying to develop sustainable proliferation resistant nuclear system, including next generation of nuclear reactor, closing fuel cycle, eliminating high-level waste that we right now have because we didn't do any reprocessing, offer developing countries nuclear energy with energy security. Also, the next step is develop high-temperature nuclear reactors. If we go to much higher temperature, efficiency of thermal to electrical will go up to maybe 50 to 60%. And also, at high level of temperatures, the outlet temperatures will be high enough for hydrogen production. And this is some additional thing that we need to do. So generation 4 was discussed on international level. Many countries were involved. And they discussed and they have chosen these 6 types of reactors to be developed in this next generation. Several countries took lead and picked different type of these reactors. And I will show in a minute a diagram. So this is the diagram of 6 types of generation 4 reactors, including sodium, fast reactors. Some of them are fast, some of them are thermal. Fast and thermal basically talk about the energy, dominant energy of neutrons inside of the nuclear reactor. Sodium, as you can see, it's coolant. So what we are using to cool off the fuel. So this is liquid metal. We have gas as well. So these are gas-cooled reactors, very high temperature gas-cooled, and so on. We still have water-cooled reactors and molten salt-cooled reactors. Again, application could be for electricity production, for minor actinide burning as well, plutonium burning, electricity or hydrogen production, process heat. We could also use the heat for all kinds of purposes, and so on. And some of research and development that will be needed, particularly materials at so-called extreme conditions, including very high temperature, high pressure, as well as high radiation fields. So we still need to do a lot of work in that particular area. And I will just show a few of those. So this is high temperature reactor. So this is very high temperature reactor. So this is one of the favorite for this country. Another one, this is gas-cooled fast reactor. So you have the characteristics. I will not go over that. But what is interesting, and I will show in a minute, The fuel are small coated particles, about 1 millimeter inside. So because fuel is in the middle and it's surrounded by ceramics, so it could sustain extremely high temperatures. This is lead-cooled fast reactor. Again, interesting design, and our department has been working on lead bismuth cooled reactors. This was designed on Russian submarines, among the other things. The issue with this one is that the core life cycle could be 20 to 30 years without refueling. So you can run it as a battery, you plug it in, you run it for 20 to 30 years without refueling, you take it back and plug the new one. So it reduces considerably the amount of spent fuel or radioactive waste. And again, we need new materials that could sustain 30 years without any type of replacement. This is sodium-cooled fast reactor, which is also envisioned for minor actinide and plutonium burning. And let me just go quickly over. Supercritical water reactor and molten salt reactor. We do have in our department another group, including Professor Peterson, who is working on molten salt type of reactors with fuel in form of pebbles. Okay, so you are floating pebbles, and this is also a very neat design because of high temperatures that it can sustain. So in terms of advanced fuel cycle, recycling and whatnot, if we have this once-through type of the policy, which was no recycling, just take spent fuel and put it in underground repository, you will see how many repositories we would need to build if we would to include new construction of new nuclear reactors. We had problems to build one. It is taking more than 30 years of fighting, mostly political fighting. So imagine if we were to build another one and another one, it would never happen. So if we recycle and reprocess and burn these minor actinides and plutonium, we would need only one repository regardless of number of reactors that we might build. Why? Because what we will be putting into repository will be just fission products that will decay in few hundred years. Instead, if we have uranium and plutonium and all the products and minor actinides that could be active over a very, very long period of time. So these are some of the processes that are under the development in this country. The one that is almost chosen is UREX 1A, in which uranium is separated, technetium, these are some of the products, and plutonium. The issue in this country is no separation of plutonium. There is Purex process that is being developed, and other countries, almost every other country is using that one, but it does separate uranium, it does separate plutonium, and everything else will stay together. So it's not politically correct in this country to do that, so we have to develop a new process. In terms of Yucca Mountain issues, so currently we have 120 sites in 39 states with spent fuel distributed across the country. Okay? If safety is an issue, I think it's much better to have one place in which we store all that spent fuel. So there was all kind of fighting about Yucca Mountain. A lot of money was spent on that. Nevada Senator Harry Reid will basically do everything in his power to stop construction of Yucca Mountain. However, this is milestone and outline. So the Yucca Mountain project has been accepted and supported by the Congress. President signed. DOE is just about to submit application for license to Nuclear Regulatory Commission, probably sometimes in June. And then everything is up to NRC, so we expect in the time frame of 3 years that NRC will review it and give permission for authorization for construction, and this is the rest of the story. So in terms of what we have in Yucca Mountain, okay, so this is the site. It's very dry, and the tunnels are drilled inside of Yucca Mountain, and this is kind of the system, dry shield, waste package that will be packed. And right now, the application for license is submitted assuming that there is no reprocessing. So the packages will be just packed on the ground. But if anything changes, it will be very different. This is advanced burner test reactor that is supposed to burn plutonium and minor actinides. This is a high temperature nuclear reactor that has all kind of interesting applications, including high temperature process heat for hydrogen production, electricity production, downstream operations, and whatnot. What is also interesting, and you probably heard about issues with oil sands, oil shale, and whatnot up in Alberta in Canada. So process heat from nuclear power plants could be used to actually melt that oil from sands or shale and just pump it. Also, it could be used to process and produce hydrogen that is also needed for future refineries, thus reducing reliance on natural gas and what is very expensive. So this type of high-temperature reactors could be used for electricity production, for heat, and for hydrogen production. They could use all kind of fuel and could be used for reprocessing of fuel and burning. These are triso particles, and I have the picture of it. So this is 1 millimeter in diameter triso particle fuel in the middle. These are different layers of ceramics. So you put many hundreds of thousands inside of this pebble bed, which is about 6 centimeters in diameter, and then you place it in the reactor core. So it's and cooled by gas in this case. So it's a very interesting system. It has 45% of thermal efficiency. It can go to very high temperatures. The other US type, General Atomics type of design includes instead a graphite block, which is a moderator, and then these particles are stuck in some type of cylinders. This is the idea how to use these high-temperature gas-cooled reactors to produce process heat, hydrogen, and electricity. So you have the nuclear power plant, you have electric power going in one direction, you have process heat, you have high-efficiency hydrogen production, and then you have hydrogen distribution infrastructure on one place. This is the timeline for hydrogen initiative. Hopefully, nuclear energy will be included in that. And let me just show that thermochemical process. Okay, so this is hydrogen production. It's still under research and development, and this is just in both Idaho and General Atomics. So this is you need to have 800 to 1,000 centigrades of heat. You need different type of chemicals that are mostly recycled. You need water, and then you produce hydrogen and oxygen in this process. And I will just say a minute on these small-scale reactors I already mentioned. So this is the one that has been developed in our department. So very simple design. No pumps, no pipes, no valves, factory fueled, sealed, 20 years at least of core life, no fueling on site, and its small module could be up to 100 megawatts or so. that is transportable. And what is interesting, depending on type of cycle that we use, it could be used to breed more fuel, which is the line up. These are the years. It could be used to burn fuel, or it could have a regime in which the amount of fuel that is spent and fuel that is burned is about the same. So it can run in a constant regime for many, many years. So this is my vision of sustainable nuclear energy. Emission-free, safe, and reliable. We need to close the cycle. Just put basically fission products in geological repositories. This is also new fuel cycle, which is proliferation resistant, and new simplified designs for next generation of reactors, production of electricity, hydrogen, use it for water desalination, district heating, and whatnot. And this is the end. So thank you very much, and I hope there will be time for a few questions.